Okay, hello everybody, and by everyone I mean no one, because no one is here right now. Unlike a normal live recorded lecture, this is a unlive, dead recorded. That's not a good word. This is a not. There's no audience here. Is the point? Audience. There's no class here right now because I am refilming a lecture that was supposed to do Monday, but there was technical errors. I sound like a robot. My hands were teleporting all over the place, and so I'm going to redo the very last proof we did. And that had everything to do with this awesome theorem that's called fundamental theorem arithmetic, one of my favorite fundamental theorems. And what that says is that every natural number can be written uniquely, up to ordering at least, as a product of primes. And this is surprisingly kind of simple to think about because, of course, if you take any number, like say 48, take a number like 48, say, right? And you can divide it, right? 48 divides into pieces. You can divide it into, let's say, 6 times 8. And then that 6 divides into pieces. That's 2 times 3. And that 8 divides into pieces. That's 2 times 4. And that 4 divides into pieces. That's 2 times 2. 2 times 3 times 2 times 2 times 2, right? And then we stop, right? Once you hit primes, you stop because you cannot divide primes into more things because into more like non-1 numbers, right? Because by definition, primes are only divisible by themselves or 1. So it all works out, right? So kind of course, right? If you keep dividing a number into smaller and smaller parts, you eventually reach the primes. The primes are basically the atoms of numbers. Through where all numbers are built on. And if you go any further in math, you'll see exactly how important they are. They're awesome. But the point is, the fundamental theorem says that not only can every natural number be broken up into primes, like there's of course they are, but that's unique. And that one's a little more interesting because that's not always the case, right? When you're just splitting up numbers. For example, 20 equals 2 times 10, but it also equals 4 times 5, right? So 20 can be written as the product of two integers in multiple different ways, right? At least these two ways. But these aren't primes, right? It can only be written as the product of primes in one way. When we say both these ways you can write it as the product of integers will lead to the same prime decomposition, the product of primes. This is going to be 2 times 2 times 5. This is going to be 2 times 2 times 5. So the point is, it all works out, right? Numbers can be written multiple ways as a product of integers, but as a product of primes, only one way, and that's called the prime decomposition. That's where we're starting. Hope this makes sense. Good? Get the same response I do in a normal lecture. Nice. So, let's do an example of this and try to prove the following claim. Or prove just, okay, give it away. I was going to say prove or disprove. Let's prove. The claim is for all A in the natural numbers, 5 divides 32A. Oops. 5 divides 32A. We'll only do one direction. Or implies that 5 divides A. Now that's kind of interesting, right? We could also do the reverse direction if you ever want to save some work. The reverse direction really is going to be super easy because the reverse direction, all that's saying, oh, is it blurry? Hello? We'll probably come back. The reverse direction, all it's saying is, like, if we had this way, that'd be saying that 5 divides A implies 5 divides 32A. Oh, it wants to come back. It wants to come back. But anyway, clearly this is true, right? Because if you can split A into even groups of 5, well, you can split 32A's into even groups of 5, right? What you can see that is that this means that 5 equals, nope, this means that A equals 5K for some integer K. And so then 32A would equal 32 times 5K, which equals 32K times 5. The point is 32K is an integer, since K is an integer, and integers are closed under multiplication. So clearly, if 5 divides A, 5 is going to divide 32A. The other direction, though, is not so simple. Not so simple at all, right? If we start from 5 divides 32a, if we use kind of, I'll use green. Whoops, black is serious. If we start with 5 divides 32a, if we did kind of the same idea, we just did the same kind of logic, what we'd get is we want to say that, and then notice that a equals 1/32 32a. And then here's 5 divides 32a. 32a equals 5k for 700k. This is going to equal 1/32, 5k, which is going to be k 30 seconds times 5. And so this will be a multiple of 5, a will be a multiple of 5 only when 32 goes into k, where k divided by 32 is an integer. But why is that? Right, this is a very different ballgame. We cannot use the same logic we just did. So let's get to thinking. Let's go to the drawing board. That was all on the side. Let's write it down and make this an official scratch work. So for the official scratch work, let's see. Maybe there's a reasonable value here. I wrote down fundamental arithmetic. So let's just start with what we know. Right, if we're going this direction, right? Let's assume we have to assume that 5 divides 32a. My 5s look like s's. By the way, when you guys were in school, did they teach you to write 5s like that, like all in one motion? Or I had one teacher try to tell us to do. You do that, and then you add the tip. Which, oh my, that actually looks kind of cool. Oh, that's when people get the really small curly 5. Anyway, sorry. So the point is, I just realized something about calligraphy. But anyway, if you assume that 5 divides 32a, what that means then is that there exists a k in z, right, such that 5k equals 32a. Simple enough. And again, on our own, we can't just go straight from there to 5 divides a. But here's the thing to notice. Here is the beautiful, beautiful, beautiful bit, right? 32a is a number, right? Because it's a natural number, because since a is a natural number and 32 is a natural number, 32 times a is a natural number. Because 32 times a is a natural number, what that means is that it has a prime decomposition. Oh, the red's coming back. So what does that mean? I'm answering my questions as we go. What that means is that this is going to equal P1 times P2 all the way out to Pn for these primes. It's a product of primes. Right. But notice that 32a, 32, you break that up, that's 16 times 2, which is 8 times 2, which is 4 times 2, which is 8 times 2, which is 4 times 2 times 2, which is 2, I missed one. I'm sorry. 32 is 16 times 2, which is 8 times 2 times 2, which is 4 times 2 times 2 times 2, which is 2 times 2 times 2 times 2 times 2. Right? It's 5 2's multiplied by each other. So what that means is that 32a equals 2 times 2 times 2 times 2 times 2 times a. Right? Here's the point. If 5, the prime number 5, divides 32 times a, right? That means 5 must be in this prime decomposition somewhere. Right? Because if you break 32a down into primes, apparently 5's there because 5 divides 32a. And so what that means is 5 is one of these primes. But 32, only that contributes, it's 5 2's, none of which are 5. That's unfortunate. But you see what I'm saying? They're all 2's, no 5's. So that means whatever prime in here is 5 must have come from the decomposition of a. So 5 must divide a. That was a lot of words. Let's write symbols instead. Visual learners, listen up. Kinetic learners, I'm sorry, I'm kind of screwed. There's really no movement in this class. But the point is, yeah. So 32a So let's look at, for example, let's say, I'm going to redefine the p's. Let's say the a p1 times pm. That is the prime decomposition for a. And then k is a natural number as well. So k is going to put a prime decomposition, let's say q1 out to qs. Then, notice, because 5k equals 32a, substituting these in, we get 5 times q1 times q2 out to qs, that's substituting the k in, equals 32, which, by the way, you can write as 2 times 2 times 2 times 2 times 2 times the a, p1 times pm. I'll say these are primes and these are primes. The point being, both sides here are products of primes, right? The q's are defined to be primes, the p's are defined to be primes, 2's prime, 5's prime. So both sides here are products of primes. So these are both the prime decomposition for 5k, which equals 32a. So these are prime decompositions for 5k, which equals 32a. They're prime decompositions for the same number. And because prime decompositions, where is it, are unique up to ordering, what that means is that these are actually the same, just reordered from each other. So the same primes show up here as they show up here in the same numbers. So that means we're done. That means this 5 right here, right, must show up somewhere in the prime decomposition here on the right side, since they're the same decomposition, just ordered. It's not going to be any of these 2's because 2 isn't equal 5. That means 5 is in this set of P1 to PM. The 5 is in one of the primes in the prime decomposition of A. Well, what that means is that A, right, is going to equal P1 all the way out to PM, but 5 is in there somewhere. This is like P1. At some point we have a 5. We keep going, you get the PM. 5 is in there. So that means A is an integer multiple of 5, right? A is 5 times something, whatever P1 is P2, that's PM, all that stuff except for what 5 is. So that means 5 divides A. Brilliant, 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 right? And this all relies on the fact that 5 is prime. Yeah, because if 5 wasn't prime, then we have to break it up here in the prime decomposition, it would all fail. So, let's get started. So, go ahead and prove her. Proof. I recently super glued these together, so this is awesome. Proof. So we're not doing indirect proof or anything here. We're just doing a direct proof. So we're going to go straight from the hypothesis to the conclusion, or that's the goal. So the hypothesis logically leads to the conclusion. So we always do in a direct proof is we first just let everything be in the domain it's supposed to be. So let A be an arbitrary but particular natural number. And now we're just assume the hypothesis and show that that logically leads to the conclusion. So let's now assume that 5 divides 32a. All right, then really everything we do, we have a divide sign. The first thing you do, the only thing we really can do is this gives us a foothold to write an equation. The equation here is that thus, or then, too early for thus comes later. There must exist a K and Z such that 5K equals 32A. Now here's the part where we want to get the prime decomposition for K and A. So I have one problem. There's always a problem, right? A is a natural number by definition. And natural numbers have prime decompositions, that's fine. K is an integer. Maybe it's positive, maybe it's negative, maybe it's 0. Negative numbers don't really have prime decomposition. I mean, they do, we could define them, but it's a little different than this because there's negatives to worry about. But this doesn't matter here because K is going to turn out to be a natural number, right? Obviously, 32 times A, if it is a natural number meaning a positive integer, this is going to be a positive integer. Since 5 is positive, that means K's got to be positive because if it was negative or 0, then this product would be negative or 0 and it wouldn't equal 32 times A. But we just show that, right? We need to prove why we can use everything we can use. So let's note then that K equals 32A over 5. And since 32 is positive, A is positive, and 5 is positive, K, which equals 32A over 5, is positive. And that's just another one of those natural number facts you gotta know. You gotta know things with a natural number. It's how to multiply or the integers. If you multiply a negative by negative, you get a positive, that kind of stuff. Negative times positive is negative, positive times positive is positive. I just listen to them all. Yeah, so K is positive. Thus, K is in Z plus, which is the same thing as natural numbers. Natural numbers are just positive integers. Good. So now we have K is a natural number and A is a natural number, so we start to talk about their prime decompositions, and now we're moving. So then, since K is a natural number, by the fundamental theorem of arithmetic, there exist primes P1 through, I don't care, P1 through Pm. Here K is being used as the multiple of A, and so we can't use it as the index on our primes. Otherwise we're using K for different things, which we can't do. But anyway, by fundamental theorem of arithmetic, there exist primes P1 through Pm such that K equals P1 times P2 all the way up to Pm. Similarly, something like that. Similarly, since A is in the natural numbers, there exists primes, I'll call them Q1 through Qs, such that A equals Q1 times 2Q all the way out to Qs, the multiple of all the Qs. I mean, this is just what it means. This is just exactly what the fundamental theorem of arithmetic says, basically, that a natural number can be written as a product of primes. Product of primes, product of primes. The fundamental theorem of arithmetic also says they'll be unique, and we'll get to that later. It's going to be important. But right now, we just care that they're product of primes. Then, note that 5K equals 32A. Right? So, if we substitute, we get 5 times what's K? P1 all the way up to Pm equals 32 times Q1 all the way up to Qs by substitution. And this is 5 times P1 all the way up to Pm is going to equal 32. Remember, it can be written as 2 times 2 times 2 times 2 times 2 times Q1 all the way up to Qs by factoring 32. By the way, this really gets down to what the word factoring means. Factoring means just writing something as the product of two things, right? That's why we had x squared minus 1. We said we factor and we do this because what we just did, we took one thing and wrote it as the product of multiple things. But same thing with like if you wrote 10 equal 2 times 5, you just factor 10. You wrote one thing as a product of multiple things. It all comes back. Math actually makes sense. Who knew? Yeah. Now here's the thing to notice. The big thing to notice. These, both the left and the right side here, are products of primes, right? Note that left side are products of primes that equal the same number, and that is 5k, otherwise known as 32a. Right, 5k equals 32a, so they're literally the same number. So this right here, the left and the right are literally two ways to rewrite the same number as products of primes. But from the arithmetic, right, this prime decomposition, the way you write primes, is unique. Right, every answer will be written uniquely of the ordering as a product of primes. So that means that these are really the same products, just reordered. So I'm gonna erase up here. All right. If we continue this, remember what we had written down. Oh no. Do some refurbishing here. There we go. Look at that, I wrote it. Proof continued. So what we're at is that 5 to P1 all the way back to PM, and 2 times 2 times 2 times 2 times 2 times Q1 times QS, right? That all, they're both prime decompositions for the same number. So continued. Observe that 5 times P1, or actually we kind of already wrote that. So I'll say, since prime decompositions are unique for any integer, five P1 out to P1 PM must be the same product as 2 times 2 times 2 times 2 times 2 times Q1 out to QS, just reordered. Because if they weren't the same product, just reordered, that would mean that there's a number, a natural number, that you can write two ways as a product of primes, which I already talked about, it's impossible, but from arithmetic. We didn't prove it, by the way. But that's for number theory class, which I wish this was. Number theory is great. But anyway, next year. So, yeah. So, they must be the same product, just reordered. So what that means, thus, this prime 5 has got to be in here somewhere. It must be in this set of all these primes here. It's got to be either a 2, or it's got to be whatever Q1 is, whatever QS is. And notice I don't have to write 2 5 times because a set, like something's either in or out of a set. It can't be in it multiple times. So the 2 here just means 2 is in it. What I'm saying is 5 must be one of these primes. Note, since 5 does not equal 2. 5 must be in the set of Q's, the set of prime factors of A, right? Thus, 5 equals Qi for some I in the index, the indices, right, which go from 1 all the way up to S. So 5's got to be one of those things. Therefore, A, which remember, the Q1s were defined to be the prime decomposition of A. So A equals Q1 all the way up to QM, or sorry, QS. And we know that 5 is in there somewhere. This is going to be Q1, there's going to be a 5 in that product somewhere, times QS. And then notice, this right side, which equals A, is 5 times a bunch of stuff, a bunch of primes, which are integers. Then, since primes are integers, and Z is closed under multiplication, A is an integer multiple of 5. And then here's the big thus. Thus, 5 divides A. As desired square, we are done. Yeah, that's it. I mean, that was pretty amazing. That's what, like, the fundamental thing we're going to take actually allowed us to prove this thing we could never prove before. Actually, you can prove something called the division algorithm, but for our class, right, we can never prove this before. And that's has to do with the fact that these natural numbers can really be broken into their atoms, which are prime numbers, and that tells us everything, right? Because if 5 divides 32A, that means somewhere in 32 times A, and the atoms of that number is a 5. But it can't be in the 32, because the atoms of 32 don't include 5. So it's got to be in the A. That's what this whole thing just proved. Any questions? If so, email me or whatever, because no one's here right now. But anyway, that's it, everybody. I will get this online as soon as possible. You guys, I mean, I guess if you're watching this already online. So yeah, enjoy the rest of the videos this week. And next week, we start some beautiful, beautiful proofs. Next week, we're going to make some mathematicians out of you. All right, so I'll see you there, everybody. Have a great weekend, a great day, great everything. Bye.